Welcome to this fourth session, and today we will talk about convolutional layers, and especially, so this was a topic already of previous sessions, but today in particular we will concentrate on spectral, so on convolutional layers based on spectral methods. And as usual, this notebook is, you can find it in the Git repository, so you can download it. So the tutorial today is mostly theoretical, and the reason is that on the implementation side, so we will see something on the implementation at the end, but the goal is to understand why these layers are defined like they are defined, and in the end the implementation will just be a special case of the message passing architecture that Antonio described so well last time. So in terms of implementation, the only task is to specify a couple of things in that implementation that we have already. Okay, so the outline today is first to give a very brief, so there is plenty of things, we could have a sequence of tutorial only on this, but just some idea of why convolution are used in machine learning. And then I would like to discuss some theory on convolution. The idea is that, so I hope to convince you, if you don't know it already, that convolution is a nice thing to have deep learning, machine learning model, but then having it on a graph is not immediately clear. So how to extend it to work on a graph is not immediately clear. So we need some theory to see what can be extended. And then once that is done, I will talk about how to use this theory of convolution on graphs to define some convenient layers in Pytorch Geometric. Okay, so let's start. So the basic idea of convolution is that there are two properties. One is that we can have weight sharing, so have less coefficients, so equally powerful models, deep model, but with less coefficients. And the second thing is that this is done in a way, so not just by dropping weights, but also by having some structure embedded into the weights in a way that we are able to detect translational invariant and local features within our input. So just as a brief idea, this is a picture of a fully connected architecture. So the input is in this case a 5-dimensional vector, and then there is a layer of 6 with 6 dimensions. And here every input is connected to every element of the first layer. Okay, so it's fully connected in the sense that a change in every one of the inputs, so of the dimension of the input, will affect all the dimension of the intermediate layer, and the same is for the next layers. So one idea would be to have something like this. So this is an abstract depiction of a convolutional neural network. So the idea would be to have just a bunch of weights, so like these 5 weights, and then to have them shared across the other nodes. So like we take these 5 weights, so these 5 weighted edges, and then we move them around in a way that so still we have something that looks like a fully connected layer, but the same 5 weights in this case are shared among different nodes. Okay, and this would be good just to have some weight sharing idea, so to have less coefficient to learn. But this can be done in a very clever way using convolution, and this is typically used in computer vision. So when the input is an image, and actually is one, so convolutional layers are one of the main reasons that, or at least one of the fundamental reasons why computer vision works so well. And the idea is something like that. So if you have an image, so a square, or not necessarily square, sorry, a matrix of pixels, here they are integers, you can take, to form something like this weight sharing, you can take a mask or a filter, and you can convolve the image with this mask. So you can start by multiplying pixel-wise the element of this red box with the filter, and then in this case I think we are computing sum is 1 plus 4 plus 4, yeah, 9. So the aggregation, just multiplication times filter and then sum. Okay, and then we can take this.
Sorry.
Yes.
Can I? So when you say that you are using 5 weights,
Yes.
You mean that you are going to use the same 5 weights for groups of 5 nodes?
Yeah, for example, here in this convolution, so this convolution is a way to get that. So you can imagine this 4 number, 1, 2, 0, 1, to be 4, in this case, weights, okay?
Okay.
So this,
Okay.
if you take the first image and you unroll it as a vector, that works like your the first layer, okay? And then the intermediate layer here is just this small image unrolled, okay? So in principle, you could have that every element of the input, of the output, so this 9 could be a function of every pixel in the image, okay? Instead, what we do is to fix these 4 weights here, and we first compute this 9 by this operation, by this convolution operator, so we multiply pointwise this weight with the given inputs, and then we compute the sum, and we have this one. And then the next step is that we move this filter 1 pixel right. So now we have 1 times 2, 2 plus the times 6, 0 times 4, and 1 times 3. And then we compute the sum, and this will give the second pixel. And then we continue to roll this window around, and also on the next line. So we will have the second layer. But now the weights, so the coefficient used to compute linear combinations, are shared because they are always the same 4 weights. Okay, is it clear or?
Yes, thank you.
Okay, okay. And this is a very effective way to work with images, because these, of course, is easier to memorize only 4 or to learn only 4 weights, but especially this works very well, especially in a deep architecture. So if you do this multiple times combined with other operation, but because it works locally. So the images are not just a random pixel. There is a neighborhood relation. So it's useful to have something that works locally to detect local features of the image. Okay, and this indeed works very well on images. And we can imagine that something like that works also on graph. So we have seen last time that this message passing architecture works with similar ideas. So we want to have features of a node computed based on the neighborhood of the node. Okay, so something like this, something that is only local, that doesn't depend on the entire graph, because that is computationally expensive, and also in principle we should have a good knowledge if we just look around a given node. Okay, so the idea now is to extend this to graphs, and to do that I will just, as I said, present some theory on convolution. So we do it in 1 dimension because it's easier to visualize. So this is the visualization of convolution. So we have this blue signal, which is just a square signal, and we want to convolve it with the red one. So the red one plays the role of the window that is moving. And so we do the same. So we start from the left, and every time we compute the multiplication and then the sum, and the result is this black line. Okay. And so this is, we have a 1-dimensional signal, so this is moving just in 1 dimension, direction. In the image is moving in 2 directions. And the definition of the operation is very simple. So we just take 2 signals, so 2 vectors, v and w, and the convolution vector is another vector, which is just given by that operation. So is the sum, the multiplication of, this is the formula for what the image is showing. So you just take the 2 vectors, slice them in the opposite direction, and compute the sums. Okay, and this can be implemented very easily just by writing down this formula. So this convolution operation is that one, and then we can have a test. So with 2 vectors of 20 elements, and just show you that is working. So the blue and orange points are the 2 input vectors. Here the diagonal lines are just because, so these are just vectors, so this line doesn't make sense, it's just to show that the vector goes on here. And the convolution is this green line. So we just take the orange one, we move it starting from here to the right, and every time we multiply it and take the sum. So for example, when it is here, it multiplies the blue one, but it's 0, so the sum is 0, 0, 0, and then it starts to grow and goes down. Okay. Okay, and so this is the operation of convolution, but this, as it is difficult to define on a graph because it depends on the possibility of computing translates of vectors, which is not so immediate to do on a graph. And so the idea is to go through the Fourier transform. So the Fourier transform at first, so the only thing that we need at first is that it is just an operation that maps, it takes a vector and gives back another vector. And this is, there is a lot of theory, but we just need 2 properties. The first one is that there is an inverse, so it's possible to compute the Fourier transform and then apply the inverse, and we are back to the original vector. And the second one, which is fundamental for convolution, is exactly that if we take the Fourier transform of a convolution, so this is a vector, we apply the Fourier transform, and the result is the pointwise product of the two Fourier transforms. So this is a property that comes from the definition. But this can be used, so these two properties can be used to see that the convolution between two vectors. So we use first the first property, so the convolution is equal to the inverse transform of the vector. So this is just the first property. And then we use the second property to write the transform of the convolution as the product of two transforms. Okay? So we have a very simple way to, I mean, at the moment it's not clear why this is simpler than just using what I showed before, but it is an exact equality. So the convolution is equal to the inverse transform of the product of the transform. And we can see that with two random vectors. So this is the convolution as computed above. And then you can compute it as using, so FFT and IFFT implement the Fourier transform and the inverse. So you can just take the Fourier transform of the first vector, compute the pointwise multiplication with the second one, compute the inverse transform, and these coincide with what we had above. And actually, the way, so if you use the implementation of the convolution given by SciPy or NumPy is given, I think, exactly in this way. So here I'm taking the absolute value because I show you, so in principle, this is a complex valued operation. So there is also a complex term, but they are all zero, you see, or almost zero. So here we are just creating some confusion. So on the graph it will be real valued, but here we can remove it and you see that we have this equality of the two operations. So this is really an equality, okay? And then we can go on. So we have this operation, and this can actually be defined in a very simple way. So it's actually given by just a matrix vector multiplication. So if you take a vector to compute the Fourier transform, you just need to compute the matrix vector product with respect to this matrix U. And at the same way, the inverse transform is given by the conjugate transpose. So it's the transpose and then taking the complex conjugate because the matrix is complex. Again, it will be real on graphs. And then there is a normalization factor. So here, so there is a lot of analogy between this Fourier transform and the one on graphs. This normalization factor in front depends on, so it will be possible to define the Fourier transform slightly different and have a different normalization. So this one divided by n is not very important. What is important is that in the vector case, there is a closed form expression for this matrix U, which is just a square matrix, so n times n, and is given like this. So every column is given by a function u0, u1, un minus 1, evaluated in 0, 1, up to n minus 1. Okay, so if you change column, you change the function. If you change row, is the point 0, 1, n minus 1. Okay, and the function are given, so they are known, and they are just given by the cosine minus imaginary unit times sinus, and then the argument is something that is just dependent on the size of the vector, and then the variable x is exactly the one that you evaluate here. But it's not very important what is the expression for these functions. What matters is that it's very easy to form the matrix U, and once you have the matrix U, it's very easy to compute the Fourier transform. And we can see that, so this is just the definition of the matrix U, and then the Fourier transform can just be defined by computing the matrix U and multiplying the vector, and the inverse transform is just the conjugate transpose of this matrix multiplied by V and then divided by n, because we had that normalization factor up there. Okay, and let's see if it works. It should work. And indeed, if we compare the Fourier transform, the one provided by SciPy, with our implementation with matrix vector multiplication, it's, you see, it's not 0, but it's all 10 to the minus 15, 16. So it's essentially 0. And the same thing for the inverse Fourier transform. So the official one compared with our matrix vector implementation is essentially 0. Okay. So far we had that there is this convolution operator that we want to extend. We have this nice property in terms of Fourier transform, and we have a way to compute the Fourier transform. And we are almost done, because now these functions here are not here just because of random reason. They are here because they are eigenvalues of the Laplacian. Okay, so you can define the Laplacian on a vector, which is just given by the second derivative in this case, because everything is one-dimensional here. And if you apply the Laplacian to this function here, you get again the same function scaled by a number. So they are exactly eigenfunctions or eigenvectors of the Laplacian, okay, with different eigenvalues, but they have that property, okay. So we have a very complete thing in the sense that the idea is take the Laplacian, find the eigenvectors, use the eigenvectors to define the matrix U, use the matrix U to define the Fourier transform, and then by the Fourier transform we can define the convolution, okay. So in summary, we have these. So if we want to compute the convolution between two vectors, we can just apply, so we can just compute the product of the pointwise product of the two Fourier transforms, so just multiply by U, and then apply the inverse, yeah, here there is a divided by n missing, sorry, and then compute the inverse transform, okay? Or written in another way, if you want to, instead of using W, we can directly use U times W, as it's called G of W, and this is a filter. It's called a filter because the first equation can be written in this form. So the inner thing is just equivalent to multiply by the diagonal matrix having U of V on the diagonal. So it's exactly this one. This is just a more compact way to work. And so what we can do to compute the convolution, once again, is to compute the Fourier transform of U, multiply by a filter, and compute the inverse transform. Okay, and let's see that this is the case, and it should be. So we are just taking, I just wrote down this operation in NumPy and compare it with our original definition of the convolution, and indeed they are exactly the same. Okay, is it clear so far? Do you have questions on this before moving to the graphs?
Yes, I think you can move on. Yeah.
Okay, perfect. Okay, and now this bunch of theory was just to introduce the fact that all this can be extended on a graph. And the idea is the following: so we can all these operations, so going from the last operation to the first one, can be defined on a graph. So the idea is to take the graph Laplacian, compute the spectrum of the graph Laplacian, so the eigenfunction, eigenvectors. Then we can define a Fourier transform and use the Fourier transform to define a convolution. Okay. So let's see that. So first, in the following, I just assume that the graph is given by some node and edge, and we assume that it's undirected, unweighted, and simple. Those are not restrictions, so the layers at the end work also in the general case, but it's just easier to write everything here if we work under this assumption. So just a recollection of a couple of things from graph theory. So we can define the adjacency matrix as the symmetric matrix where we have a 1 if there is a connection between two nodes in position ij. So if there is the edge ij, and 0 otherwise. Then we can define the degree matrix, which is just a diagonal matrix where the diagonal elements are given by the degree of each node. And then the Laplacian is just defined as the difference between the two. Or another option is to define the normalized Laplacian, which is just given by the identity minus this renormalization of the A by means of the square, so the negative square root of D. Okay, this is easy to compute because D is diagonal, so the inverse square root is just given by, is again diagonal, and every element of the diagonal is 1 divided by the square root of the degree. Okay, so this is very, so up to here everything is quite cheap to compute. Okay. And then we can, so this Laplacian has a very nice connection with the Laplacian of the general case, of the vectorial case. And in particular, we can compute a spectral decomposition of the Laplacian. So just compute an eigen decomposition. So the matrix L is symmetric. So it is given in this way. So there is U, and here there is U transpose, so the same matrix. And then this lambda is a diagonal matrix containing all the eigenvalues of the graph. Okay, there are plenty of theoretical results on how these behave, but it's not very relevant here. Okay, and then so now we have Laplacian, eigenvalues of the Laplacian, and using that we can define a Fourier transform, and it's defined exactly as above. So just take now V is not a vector, but is a vector of features on the graph. So we have we just give an order of on the nodes, and then V is a vector with values on this ordered list of nodes. And then the Fourier transform of this node is just given as before by the multiplication of the matrix of the eigenvalues of the Laplacian times V, and the inverse transform is just given by the transpose matrix. So here is the difference as with respect to before. One difference is that the matrix is real, so we take the transpose instead of the Hermitian transpose. And the other difference is that now the normalization is nice enough that you can really invert the transform by using the transpose without dividing by the number of nodes. That depends on actually the definition of the Laplacian and things like that, but it's not a crucial property. But then, given that, we can go on as above and define a convolution. So if we have two signal or two feature vectors on the graph, we can compute the convolution between these two, and it's just as above. So I just copy the formula. And in particular, if you denote G of W as the diagonal of our filter, so we want to compute the V is our feature vector, and we want to compute the convolution with respect to a filter, it's just given by this. So take the vector, multiply by the eigenvalues, and so on, eigenvectors, and so on. So actually, there is nothing to do here, is everything just as in the vectorial case, okay? And this means that now we have a nice theoretical notion of computing convolution on a graph. And now the idea is to use this to build some layer that have some nice local capacity as it happened in the 4 images, okay? And now we move to the actual use of this thing, so in Pytorch. And the problem here, so there is still some work to do, and this is due to the fact that this is an extremely slow operation. So the first problem is that this operation is global, so we need to form the entire matrix A, and the entire matrix, so the entire Laplacian, which is a global option, and then is slow because we need to compute an eigendecomposition, which is usually very computationally expensive. So this is not possible on graphs of large size. And large may mean some thousand of nodes depending on the sparseness of the edges, but it's usually something that you don't want to do, and for sure is not a local property. And the goal and the way, so what we are talking about in the next is how to implement an approximation of this operation, of this convolution operation, by using a message passing architecture, okay? So in particular, we are going to see two different layers in Pytorch that implement this notion. And the first one is this Chebyshev. And I let here some link to the original paper, which is from 2016. And here is the documentation of the layer, okay? So once again, the goal is to implement, to compute in a fast way this operation. So this filtering by convolution. And the assumption here in this layer is that our filter is not just a vector, but it can be written as a function of the eigenvalues, okay? Which is completely reasonable, okay? And so, again, we don't want to compute all this. And so the paper, so the name Chebyshev is because the author decided to use this Chebyshev approximation, and they use this property. So they use this Chebyshev polynomial. So these are just normal polynomial, and they are defined in this way. So you start from, so the first polynomial is 1. So the 0 polynomial, the one of degree 0 is 1. The one of degree 1 is x. And then there is a recurrence relation to compute the next one given the previous one and the previous one. Okay, so there is just a computational way to construct these. And there is this property that was proven in another paper, I think it's from 2009, that there is this approximation property of the filter. Sorry, here is not equality, it's approximation. But essentially it's possible to approximate very well functions of the diagonal of the eigenvalues of the graph in this way. So just as an expansion of Chebyshev polynomial applied to this lambda tilde, multiplied by some weight theta k, and we need to compute this theta k. Okay, and this lambda tilde is just given by the diagonal matrix of the eigenvalues of the Laplacian, normalized in some way by the maximal eigenvalue. Okay, so 2 divided by the maximal eigenvalue times the diagonal matrix minus the identity multiplied by the maximal eigenvalue. But there is some theory, so the other paper tells us that if we compute this lambda tilde, then these can be used to approximate very well every filter on that is a function of the diagonal matrix containing the eigenvalues. And there is also a nice property, and is that of this Chebyshev polynomial, and is that if we have a matrix like this, so like our Laplacian that can be written as a product of these three matrices, then if we compute the polynomial of the Laplacian, this is equal, so essentially the t of k, every Chebyshev polynomial can be taken inside the product. So we can keep out the two matrix vector multiplication and just move inside the computation of the Chebyshev polynomial. Okay, so this is existing theory, and what they did in this Chebyshev convolutional paper is the following. So we want to approximate the convolution, and we know that it's written in this way from the theory above. And then instead of g of omega, we substitute this formula that we have here. So this is just copying the formula, and then we use the property that we can take inside U and U transpose. So we exchange, first we exchange the sum and the matrix multiplication, so this is just linear algebra, and then here we can take inside U and U transpose and use this property, and we just have this final expression, which is just a finite sum with capital K elements of coefficients. So this theta k have to be approximated, have to be defined. And then Chebyshev polynomials, and these are easy to compute, and they are applied to L tilde, which is a rescaled version of the Laplacian. Okay, so given the Laplacian, you scale by the first eigenvalue and subtract 1. Okay, and this is very nice now and can be used. And there are at least two reasons why this is nicer. So the first thing is that now the convolution, if you look at the right hand side, depends only on L tilde, and L tilde is the Laplacian. It's not the spectrum of the Laplacian, so we don't need to compute U and sigma. This should be a lambda. We don't need to compute U and lambda. We just need to compute the maximal eigenvalue. Okay, so lambda max. And the second thing that maybe is a bit hidden here, but is maybe the key property, is that this expression depends on a polynomial of degree k, at most k, applied to L. And this means that it depends on power of the Laplacian up to power k. And it can be proven that these depend only, so it's easy to see that if you want to compute powers of the Laplacian up to a certain degree k, that is determined only by the neighborhood of a node of length k, so of distance k from the node. Okay, which means that if you want to compute this convolution on a node, you just need to know the Laplacian locally around the node up to the kth order neighbor. Okay, so this is a very local operation. And indeed, all these, so we had the theoretical definition of this convolutional operation, and then introducing this Chebyshev approximation, we can have a local approximation of that. And indeed, if we have a look now at the code, so this is implemented actually. So this is the implementation of, if you click this documentation, you get exactly this implementation that I'm showing you. So in the init part, there is nothing fancy except that there is this definition of the weight, which is exactly the weight, the list of weight theta, and then there is also a bias we didn't introduce here, but you can add a term at the end. And the normalization function is just doing in a bit complicated way, but it's just computing that Laplacian normalization, so this one, okay. And especially the forward method is just so it's first taking the normalization, and then is computing the Chebyshev polynomial. So it starts from why is it x here? I should check that. Maybe they start with a different normalization, but it just go on computing the next polynomials, and they propagate by computing the polynomials of that normalized weights. And then the message passing is doing nothing essentially, because we already had the matrix multiplication and then the scaling by that Laplacian. Okay, so that's it, and this is the first and more general spectral-based convolutional layer. Then there is a second one, which is even easier. So, which there is again the link to the paper, to the documentation, and this is a simplification of the Cheb-Conv layer, and it works like that. So first we assume that k is equal 1. So this is a this layer is a linear approximation of the Chebyshev layer. So which means that the sum above now has only two terms. So we have theta 0 times x plus theta 1 And here we can assume times the, sorry, this is again wrong. Okay, yeah, there should, I don't want to correct that. So the first term is linear, so this should be 1, not x, and then the first polynomial is x, okay? And then, so this is the first simplification of the Chebyshev layer. The second one is that they assume that the first eigenvalue is 2, which is just equivalent to a rescaling of the theta weights. So this thing above can be written as this, because our L tilde was defined as 2 divided by the lambda max and then L minus identity. So if lambda max is 2, this is just L tilde equal L minus identity, okay? And then down here, by this second step, we just can substitute from L tilde, this one, and so we get this formula. So we substitute the formula for the Laplacian. And then they do a further assumption, which is that theta 0 is equal to minus theta 1. And then in the end, we have this compact expression for the convolution. So for the linear approximation of the convolution. And then finally, they do a renormalization. So instead of using the identity here, they use this rescale thing. But I don't think it's very important. What is important is that at the end, the convolution is just written by a matrix vector operation involving only the matrix A, which is not the Laplacian, it's just the adjacency matrix, and the square root of the diagonal of the degree matrix, times our signal multiplied by this theta. Okay, and this in particular allows also the treatment of, I should have said also before, it's also the case in the other layer, but this allows also the treatment of vectorial features. So here, yes, this I want to correct it. So sorry. So this is if you have an input vector which is an f-dimensional feature, so like it was discussed by Antonio last time, and the output we want it to be f prime dimensional, then we can just multiply on the right by a matrix with the correct size. Okay, and then this approximated convolution is just given by this operation, so an easy matrix vector multiplication times theta. And in particular, this again fits very well. So the full message passing implementation of this layer was the one used by Antonio in the previous tutorial to discuss the message passing structure. But as you can see, this is from the documentation, this exactly writes the last formula that we had. So we just have the edge. So this is also weighted in principle. And then we have the normalization by the square root 1 divided by the square root of the two weights. So this is just a very nice and easy message passing approximation of the convolution by taking the input features, multiplying, so doing the aggregation by this operation here. And again, this is the adjacency matrix. So all we need to do is to compute the sum, not globally but locally, just on the neighborhood of the node. Okay. And then we just multiply by this theta, and this theta are the learnable parameter. So as before, now the parameter that we want to learn are the weights of our filter. Okay, and that's it, I will say. And if you have any question, please feel free to ask. So I'm sorry that this was very theoretical, but really I just wanted to show you why we end up with this kind of formulation, and then those can be just implemented in a message passing structure as we have seen last time.
No, I liked it.
So I have actually, Gabriele, can you yes, explain again, because I got a little bit lost here at a certain point here, past approximated convolution. Okay.
Do you mean, yeah?
Okay, so we have this u times g of w u transpose x. Okay.
So the first term is clear, right?
Yeah, that one is clear. Can you unroll it for me?
Yeah, then the second term, so the first one is just a definition, so almost a definition. The second one, so not a definition, but is how we define the convolution. The second part, we just take so we assume that our g of omega is defined like this sum. So we just plug in this definition inside here, okay?
Okay.
And now this inside here is a matrix, is a diagonal matrix, okay?
Mm-hmm.
Because it's a polynomial applied to a diagonal matrix, so you just apply it on every element of the diagonal, and then multiply by this weight theta. So these are weights that should be learned, but for now, so in the math we can assume that they are given, and then they are just a sum. So this is just a linear combination of powers of the diagonal somehow. And now,
Okay, so the theta k are the learnable parameters. So basically, it's the parameters of the filter.
Yeah. So it's like saying that we want to learn the theta k is like to say that to specify the filter, we need to specify the theta, okay? So it's like parameterizing our filter over the theta. And then this is a diagonal matrix, so we can take out the sum and take in the, so this is the thing in the parentheses here is just a sum of diagonal matrices. So every term is a diagonal matrix. And then we are multiplied left and right by U matrices. And so what we can do is to exchange the product and the sum. So we can take, so this is just a number, and we can take the U and U transpose inside, okay? So the diagonal matrix is Tk of lambda tilde, and now we have a sum of coefficients times a matrix. And now we use here the property that you can throw the matrix in and out of the Chebyshev polynomial. This is the case for every polynomial, but so if you, this is related to the fact that if you take a matrix which is in this form, and you compute, you want to compute powers of L, that is exactly the same of taking the power inside. So I can show you the, let's see if I don't mess around too much. So if you want to have L squared, for example, you can take this one and multiply by itself, okay? And now the ut and u cancel. Let's see. Now the ut and u, these are orthogonal matrices, so the transpose and this gives the identity, and so the inner matrices cancel, and you just get the square on the lambda, okay? And that is the same. Yes. So since this is a polynomial, it's made by coefficient times powers, so this property holds, and then you get everything inside there. Yeah. And everything is based on the assumption that the filter can be approximated well by polynomials, or equivalently that we are happy by using polynomial filters instead of any possible filters. But yeah.
Okay, thank you.
Thank you for the question.